All right, very good. So, it's now my pleasure to introduce our next speaker, who is Peter McPhee from the National Energy System Operator, or NESO. Peter is a senior economic analyst at NESO. He specializes in creating tools and models to simulate the balancing mechanism and support long-term network planning. With deep expertise in data analysis and optimization, Peter has led initiatives that have enhanced decision-making, improved efficiency, and delivered impactful results. Holding an engineering doctorate in energy systems, he's passionate about solving complex challenges with practical results-driven solutions. And outside of work, Peter enjoys sailing, cycling, and spending quality time with his family. Very good. And before Peter comes on stage, I just wanted to spend a couple of minutes and talk a little bit about the collaborative work that Energy Exemplar have been doing with NESO. So we started the relationship with NESO about 4 years ago, and as the National Grid ESO at the time were preparing for evolving to NESO and taking a more holistic view of what the energy system looked like, what they were really looking to try to achieve was to find a model which was able to deal with the complexities associated with capturing more components of the energy system. And specifically, they had a number of teams within the original project that were running legacy models in order to be able to evaluate different decision-making processes. So they had a team which was focused around assessing network options. So what this team would do is they would look at essentially what does the grid infrastructure look like within GB, and subject to market conditions, what are the potential options for reinforcing the grid to meet the demands of the future. So this is a highly spatially detailed representation of the GB market, and here the challenge is that what they need to do is to simulate a large number of potential possible operating combinations that could happen in the future. They also had a function which was looking at the generation of future energy scenarios. So being able to have a long-term view of what the system looked like, and to be able to generate potential future energy pathways, looking at different technology additions to the system. And then there was a function which was looking at energy market reform, which is really a function which was advising around policy within the UK government. And what the objective was to try to find one single consolidated model which would allow the functions across, at the time, the National Grid ESO, to be able to have a consistent view across all of these work streams and leverage efficiency in terms of the resources that were building out these models. So, Energy Exemplar partnered with NESO in terms of the delivery of the system, and in the first instance, what we did is we did a very extensive discovery and design stage. What we did was we looked at what their existing model looked like, what their existing workflows and practices looked like, and in the first ambition was really to around how can we essentially lift and shift capabilities of what we have currently onto this new platform, which would be essentially a platform for the future. So we did an initial model build and migration by taking all of their existing data elements and migrating that over into PLEXOS. And there was quite an extensive process in terms of being able to go through the backcasting and the validation of the model itself, really looking at some quite in-depth analysis into behaviors of certain technologies, and we learned a lot about potential behaviors of storage and of hydrogen, certainly as you look at years out beyond 2035. And then there was a process where we started looking at how can we achieve efficiency from these processes by greater degrees of automation. So looking at the development of more robust data pipelines, being able to share the data practices across the various different work streams. And the entire process, it was a little more than 12 months to build out something which was functioning end to end. And we went through a reasonably comprehensive process of bringing quite a large number of users up to speed in terms of the operation of this platform from a day-to-day basis. And so what I want to do is I'd like to invite at this point Peter on stage, and Peter's going to talk about some of the unique methodologies and the innovations that were undertaken as part of that deployment. So Peter, please join me.
Hi there. So I'm Dr. Peter McPhee from the National Energy System Operator, as you've heard. And I'm really excited to be here to be able to share our journey with you in terms of the highs and lows, the setbacks, and the huge positive benefits that we've seen with the implementation of PLEXOS in our business. So it all started, we were part of, what we are now was National Grid previously. And we knew that we were going to become this independent system operator, National Energy System Operator, NESO. So in that transition, we needed to be able to actually have a software that could fulfill our requirements. It needed to be flexible, so be able to have custom constraints, the kind of degree of specifications and setup of the modules within PLEXOS needed to be there to give us that kind of degree of functionality and flexibility. Particularly important was being able to scale up with our compute needs. So previously we had a piece of software, it was bid free before, and what we found was the queuing and coordination of the queuing system of our compute was a challenge. We needed to find something that sort of filled that gap. We wanted to introduce more automation, and ultimately we needed the software to instill confidence, and we need to be able to validate it against our previous approach. So the model itself starts off as actually a day-ahead model of the GB system, obviously calculating a national price for. And in that model, we use the PASA functionality in PLEXOS, which is for maintenance, figuring out when maintenance will occur, and we also use the MT, the medium-term, and ST, short-term module of PLEXOS. Those prices and the information from the day-ahead model is then utilized by the BM balancing mechanism module in PLEXOS. And in our BM model, it's using the ST, the short-term functionality of PLEXOS. So we needed to bridge that gap between the day-ahead model and the BM model. And that's where the challenge lay. So we have a BM modeling methodology that's published, and we needed to translate that into our PLEXOS model. In the BM model, we have 37 zones splitting up GB into different areas. Between each zone, there's a boundary, and those boundaries are constraints, and we can model thermal, voltage, and stability constraints on the flows, the power flows across those boundaries. And that's ultimately what the BM model is constraining to do. Redispatch actions can occur in the BM model to satisfy those boundary constraints. So bidding off wind in Scotland, for example, and offering on CCGTs in the south, resolving those constraints. The BM model follows through from the day-ahead modeling and includes interconnector, and therefore interconnector redispatch, renewable generation, and different forms of storage, batteries, short and long duration energy storage. And there's in the day-ahead model, there's a sophisticated hydrogen model as well, so it's co-optimized with hydrogen. And that's passed through to the BM. And in the BM, we model redispatch of hydrogen electrolysis. So one of the challenges is pricing the bids and offers in the BM. And a key area there is interconnector pricing, so the bids and offers prices for interconnectors. To price those, what we do is we use the data from the day-ahead model, so the prices in GB and in Europe, and we can use that to derive, combined with the flows across interconnectors, we can use that to derive a bid and offer price for the interconnectors. So this is done in a Python tool that sits between the day-ahead model run and the BM model run. So once those prices are developed, by output via the Python tool, we then use those in the BM. There's a range of other prices that are determined in that intermediate stage as well, such as there's information on CFD, plant, and so forth that is calculated within that kind of intermediate Python stage. So I've talked about thermal boundaries, and these are like static boundaries on the network. And that's the majority of our constraints are like that. However, during the development of PLEXOS, we found that we needed to be able to model dynamically varying constraints. And these are constraints that reflect the needs of the power system engineers that have modeled and determined those constraints in another piece of software, usually Power Factory. And what they advise is that those constraints needed to change depending on the flows. So over a nearby interconnector, it's flowing as an export or an import, and that would actually change the constraint level. And that needed to be modeled period by period. So in other words, we needed to find a way to define that as a custom constraint in PLEXOS. And that was one of the advantages, actually, of PLEXOS, is that it's very, very flexible when it comes to these custom constraint definitions. It did take us a bit of time to figure out the best way of doing it, because there are a few ways of implementing it. But what we found is using the day-ahead outputs directly for the interconnector flows and using the PLEXOS formulate upfront parameter setting gave us a stable, effective output that we were able to utilize. So this then moves us on to the automation aspect of PLEXOS and the way we've utilized that. So initially, we did everything quite manually, actually. We were running this whole process, setting off runs manually because we didn't have the automation in place. And that could lead to like manual error. It took a long time. With automation, and we're using the PLEXOS Cloud CLI, for example, the API for PLEXOS as well, we're able to set up extensive sensitivity analysis and automate multiple sensitivities. And as you'll find out in our real-world use cases, it's very, very handy. And it actually unlocks a lot of capability for us. So we've got reduced manual error. As long as you've ensured your automation is set up correctly and you've QA'd the automated steps, then you can be confident it won't have the errors. And one of the other things we found is there's a lot of new starters joining my team. It's grown substantially over the last couple of years. And new starters have been able to come on board much quicker because we've got the automation. They're not having to learn lots of nitty-gritty, tiny little steps that are quite easy to get wrong, and they're able to be more productive. So this slide just brings together everything I've been talking about. It shows our end-to-end process from setting up the PLEXOS database in the PLEXOS desktop, uploading to the cloud, and then running the day-ahead model in the cloud, downloading those results, so that they can be used by the Python tool to process the prices, as I was just describing earlier. And then from that, we actually push data back to the cloud again, and then we run the BM, the balancing mechanism, in PLEXOS. And finally, we can download the solution, the redispatch. Generally, it's all of the solution data, but we care about the BM redispatch cost calculation that comes out of that process. That's just one work stream. But what we've done is we've automated it so we can run many of these, hundreds, say, overnight, and thereby run lots of different sensitivities. So now I'll just talk a bit about the use cases and what we've actually been using PLEXOS to do more recently. So as you heard earlier, there's the Great Britain is focused on the Clean Power 2030 initiative. This is where we're trying to, this is where we've got an obligation that most demand must be met through renewable generation. Inevitably, there's periods when there's low quantity of renewables available on the system, and there still needs to be some periods where there's thermal, unabated gas generation. And the constraint here was that less than 5% of generation came from unabated gas. So that's the objective of the Clean Power 2030 kind of model setup. And what we've used basically within NISO, we've used PLEXOS extensively to run the day-ahead, the balancing mechanism simulations that I've just been explaining in order to run that process. And in order to understand, are the scenarios Clean Power 2030 compliant, or do they need adjustment? Do we need alternative generation to be able to meet the target? But for my team, because we're more focused on the balancing mechanism side, and what we're concerned with is with network reinforcements. Have we reinforced the network adequately to meet the challenge of CP 2030, Clean Power 2030? And we were able to investigate different sets of reinforcements and different timing of reinforcements in order to determine, are we compliant with that objective? So basically, PLEXOS is underpinning NISO's modeling transition here. Most recently, Ofgem has kicked off a long-duration energy storage cap and floor scheme. So it's ensuring that applicants to that scheme are de-risked when it comes to their capital investment by a floor on their revenue. And NISO's obligation there is to ensure that that help Ofgem to select the correct applicants, the top applicants that have applied. So we do that by calculating, using PLEXOS, calculating things like welfare, calculating system components, and using that to determine the benefits that each long-duration energy storage applicant is going to provide. And as you see on the slide, PLEXOS is again central to that. The day ahead, the balancing mechanism, the end-to-end process that I've described, the automation is all key to being able to achieve this. And there's a chart there just showing how the balancing costs come down as the duration of storage increases, and that helped us guide an advisory decision on setting an 8-hour long-duration energy storage duration target for the scheme. So finally, just go through some of the lessons learned. I think one of the key things is that well-designed tests are absolutely critical to the success of the implementation. As you heard, we've got these constraints defining our network. And we normally, of course, we apply these constraints to represent thermal constraints between different zones. However, what we did is we tried out a test where we relaxed all those constraints, and we looked at what the BM costs were with all of the constraints relaxed. And of course, you'd think, oh, that should be 0 because there's no constraints that need to be satisfied. But what that test found is actually sometimes there's non-zero redispatch costs. And that was a flag that there was a problem somewhere. There's a disconnect between the day ahead and the BM. So, for example, a good example would be the prices in the day ahead may not be being passed across correctly to the BM. And that test was able to detect that issue. And in fact, there was a case where the hydrogen price, the shadow price of hydrogen being used in the day ahead, was not being output in the same way as to show shadow prices, actually outputting the delivered price of hydrogen. And so when we tried to use the delivered price of hydrogen in the BM, of course there was an offset. As soon as we discovered that issue, everything clicked into place and it worked well. Other lessons learned is calibration and validation, so validating against previous software and ensuring that it's lined up and understanding the differences. You can't be perfect. You can never get it perfectly lined up, but you can understand where it's different and why it's different. Modeling what matters, so these custom constraints, for example, and understanding what constraints and how you want to set those up front is important. The sooner we invested in automation, or got involved more in automation, the better things turned out. So again, I'd echo the fact that automation is important, and consider that in your design when implementing and going on a journey such as this. So that concludes the slides. I hope you enjoyed listening to the journey as much as I've enjoyed modelling this. At that point, can ask for any questions, or feel free afterwards to ask me questions in the coffee breaks.
Thank you, Peter. I think that's was really insightful in terms of some of the nuances that you've undertaken in terms of that redispatch modelling. I know that there's a lot of interest now, certainly from the market participants, in terms of being able to have a better understanding of what's happening as it relates to secondary markets. So with that, would like to open up. I think we have time for a couple of questions. If anybody has some questions that they'd like to ask to Peter, I can see one in the middle of the room there.
Hi, I'm from Iberdrola. My question is related to the constraint and stability constraint you are using, because mainly it will depend on the network you choose to use. And then how you do for the forecasting network. Because if your constraints are based on 2025 network, then the 2013 network may disable any constraints related to, because it is already solved by the network. So
yeah.
How do you choose which constraint you keep and which one you disable in each network?
Well, the constraints themselves are determined by power system engineers, typically using something like Power Factory, and they use that to calculate the constraints on the network. We try to ensure that the model, the scenario that they're using is the same as what we're using. So that creates a consistency there. And in doing that, we ensure that the constraints are valid for our scenario. And we are listening to advice from power system engineers when setting up those constraints, because there is you have to consider the most relevant binding constraints from the power system perspective and translate those across to something that can be modeled in PLEXOS. There is an interface there to connect the two. You're right.
Thank you.
Okay, I think we have time for maybe one more question.
One more,
I can
yeah.
see we have one over here at the back.
Hi, Sean John, Siemens Energy. I think you sort of just answered the question. I'm interested to know if there were any complications with redispatch for grid stability in some cases. I know sometimes that can happen in the balancing mechanism, but was that considered in the model?
So we work, it was kind of answered before. We work very closely with other power system engineering teams that consider the stability issues directly in a product that's focused on stability issues. So if we know there's an area of the network that suffers from stability concerns and there's a reinforcement occurring there, or we're trying to determine that, then the power system engineers will be modeling that at that level of technical detail. Okay.
So, Peter, I have one more question for
Sure.
you. So, as I mentioned, when you started the project, you had a legacy tool and you were looking to do a lift and shift of that model into the new platform.
Yep.
And I think that as you sort of went through that journey, you probably had a number of realizations in terms of, had I have known X, I would have approached things a little bit differently, perhaps from an architectural perspective or from a data pipeline perspective.
Yeah.
So I just wanted to ask you, what are the sort of the key learnings, if you were to go back and do the project again and you were thinking about building something more holistically across the teams, how would you approach things differently?
Yeah, I think being upfront with the automation and planning that in earlier on, I think is going to be key to that, so that you're getting the benefit of automation sooner. I think, as I say, well-designed tests are important. But I think one of the really key challenges with moving across from any product, in our case it was bid-free, to PLEXOS, is getting the alignment of, say, prices in each period for the same model and lining that up. And I think it's about allocating time for that and working out what's kind of a credible kind of threshold to accept as an acceptable kind of tolerance. I think that's kind of important.
Okay, excellent. In which case, I think that if we can give Peter a round of applause.